Welcome back. This is the second talk in this sort of advanced series. This is making the jump from batch streaming Beam primitives. Before we get started, this talk is going into specific Beam primitives for streaming pipelines, how they're used, how you can configure different settings. If you want some explanations as to why you would want or need to use these things, you should watch the first talk in this series, making the jump from batch to streaming, motivations, and concepts, before jumping into this content. If you are already familiar, feel free to stick around, but I think that talk has some very good context. So this is going to be probably the most surface level thing we explain here, is that reading data from streaming sources is a little different than reading data from bounded sources. If you're familiar with Beam, you may have heard the term splittable DoFun before, or SDFs. These are transforms that provide information to the runner about the work being done, usually with the two key things being how much work there is to do and how much work has already been done. These allow for splitting that work, which is why they have their name. The idea is that you can rebalance your work on the fly if things are taking too long, or if you have more workers, you need to scale up, things like that. SDFs are really important for IOs, and more importantly, streaming IOs, because when you're reading data, you want to be able to ingest that data into your pipeline quickly. Or in the case of a streaming transform, you want something that can self-checkpoint. So self-checkpointing refers to the idea of an IO splittable DoFun to stop ingesting data and signal to the runner to resume its operation later. For streaming cases, this is, an IO hasn't gotten data in a couple minutes, and we're going to choose to checkpoint and have the runner sort of circle back to that DoFun to check for more input later. This is not something you really necessarily need to know. A lot of Beam IOs are splittable DoFuns and support self-checkpointing. The Go, Java, and Python SDKs all support self-checkpointing DoFuns. So this is really just an implementation detail. But in some SDKs, there are IOs that have SDF implementations and more typical DoFun implementations. Always opt for the SDF. That is the pro tip I'm going to give you. Always choose the SDF. Oh, generally speaking, you want to use IOs that are splittable so they can split out to multiple machines and self-checkpoint, so you're not wasting computational resources waiting for data. You don't just have one machine streaming these things in. Beam provided IOs follow this pattern, as I've said. The Java implementations are typically the gold standard for IOs. They're the most mature, they're the most heavily developed, they're leaned on a lot for things like data flow templates. So like I said, check for the SDF implementations. Usually they're called out. Always read your doc strings just to make sure, because you don't want to have a performance bottleneck in your pipeline because you've used the wrong IO. So now we'll get into something that I touched on in the previous talk that I want to get into a little bit more: windowing. So as I said before, windowing types, we have the global window, we have interval windows, and we have session windows. So the global window is one large single window from Unix time 0 to the maximum Unix time. By default, Beam operates within this window until told otherwise. So generally speaking, if you want to operate in the global window, you get it for free. You don't have to do any extra work. But that's not the interesting case. We want to talk about if we want windowing. And so fixed interval windows are windows of a fixed length that occur at the same interval. No gaps in the windows, no overlap. How you'd use that in Java, we have a P collection of strings, and then we window into fixed windows with a duration of 60 seconds. So this is a 60-second interval window. And then this is what interval windows look like. It's important to note that typically when you're dealing with windowing, you are also applying things per key. So you can see this is a 30-second window duration example. Across each key, you have window 0, 1, 2, and 3. Regular intervals, no overlap. Each key gets its own definition. This graphic is from the Beam programming guide, as will the rest of the window graphics be. Sliding interval windows, you have a fixed length and a fixed period, but the period is less than the length. And so you have a series of windows with some amount of overlap, data existing in more than one window at a time. Similar setup code-wise as you would do before. You use the same window into transform, but instead of fixed windows, you have sliding windows of duration, 30 seconds, and then you set your period of 5-second intervals. So in this case, you would have a sliding window starting every 5 seconds, but they're 30 seconds in length. This is the complicated example of 60-second windows with a 30-second period. So you wind up with overlapping windows. In this context, you have from 0 to 60 is a window, from 30 to 90 is a window, from 60 to 120 is a window, and so on. And so you have these sort of bounding boxes showing where the overlaps are. So the elements that are occurring from 30 to 60 are actually in 2 windows at the same time. Same thing as you go down. That way you get sort of that gradual transition of your data. You can look for like smoother trends over time, etc. Session windowing is the weird one. And I talked a little bit about this in the last talk, but it doesn't hurt to reiterate. You're doing a dynamic windowing approach characterized by windowing events that occur with a length of time shorter than some timeout occurring between them. These are functionally in the background treated as merging windows. So you have a series of sliding windows that are factoring in events. And then if you have 2 adjacent windows with events in them, you actually merge them into a single bigger window. Under the hood, this is pretty complicated, but if we look at the code, it's relatively easy to apply. You once again use the window into transform, but this time you set a session windowing strategy with a gap duration. In this case, 600 seconds was the choice, with the idea being that if you have 2 events that occur within 600 seconds of each other, or 10 minutes, they would be treated as being in the same window. So if we have something here, you can look at events happening in sessions. This is without per key, and each key gets its own windowing treatment here. So key 0, for instance, you have a first window, and then the minimum gap duration is exceeded. So the next slate of events happens in window 1. Similar thing, a gap, you have window 2, another gap, and then window 3 here, you do have gaps in your data, but they are smaller than the minimum gap duration, so all of this data winds up in window 3. You can see similar behavior for that with key 1. You only have 2 windows produced because there's only 1 sufficiently large gap. Same with key 2, you have 2 sufficiently large gaps that turn into 3 windows. So that's a quick overview of windowing. Now we get into something a little more complicated. We get into watermark estimation. So watermark estimation in Beam is set per data source. Each one has its own strategies and methods on how to estimate the watermark. So those are, tuned somewhat, but remember, we're leaning on heuristics to estimate watermarks, and we can almost never be perfect. Like we addressed in the last talk, there are many reasons data can be late. There are many potential issues that can arise. So we have to accept that we're not going to be perfect. But you can set custom watermark estimation, but generally speaking, it's better to let the Beam side choose that per data source. But what you can talk about are triggers. This is a very Beam specific mechanism for operating on Windows now. So what is a trigger? Triggers are a Beam mechanism that declare when the output for a given window should be materialized relative to an external signal. Triggers can be configured to fire multiple times. You can update your output over time depending on data coming in. And this is how Beam handles revisions to data or data that comes in late, is you are setting triggers. And then when a trigger is activated, the materialized output for a given window is a pane. We do love our cute naming here. So you output a pane that it encapsulates the data that is produced by that trigger. Multiple panes can be output for a single window as processing continues, and then you have to handle those as you go. So some common trigger types, there are repeated update triggers. where you output the pane repeatedly for a given window. Either you're getting, new records, or some amount of processing time has passed before you've gotten a new record. Generally speaking, using these triggers requires some balancing of latency and cost, because if you're doing a very expensive transform and doing a very expensive calculation, and then you're using a repeated update trigger, you could be doing a very expensive calculation over and over and over again. So you do have to keep that in mind. Another common type of trigger is a completeness trigger. The output gets materialized when you have some threshold of completeness reached. Usually this would be on the watermark, advancing past the end of the window, for instance. But this is also how you could handle late or missing data. Is you get something late later, your pane is now more complete, so you have to re-emit. Quick code example of this for watermark completeness in repeated update. Of course, because you're dealing with triggers, you have to have things windowed. So in the watermark completeness case, you are applying a window into transform, and then also applying triggering to after the watermark materialize that output. And then in the repeated update trigger case, this configuration is doing the same thing, same fixed windows, but instead of triggering after the watermark is complete, it's going to trigger every 5 elements. So you get 5 more elements in, you re-emit the pane. And then, okay, so we've got the triggers, but how do we handle late data after we've emitted panes? Well, in the case of completeness triggers, we of course want some level of handling, because in theory, we've emitted the pane thinking it is complete. Now it's not. What do we do? And this is important because we don't want to repeatedly recalculate panes for old data. If we have to do this regularly, part of the problem is you have implications for things like caching and garbage collection, because to recalculate things with panes, you are holding on to the value of things in those panes. And so the longer you are accepting late data and the more you recalculate, that's memory incursion cost, and you're still adding the cost of recalculating pane values on top of that. So Beam provides an allowed lateness option. So this is a concept where you determine how late you will allow data to be and still be included in your output. Allowed lateness is relative to the current watermark value. We're not keeping up with processing time. It's just how far behind the watermark will we allow data to be. Keeping up with processing time is hard. You're doing wall time. Don't want to deal with it. So this is a simpler abstraction. So relatively simple thing here. We have similar P collection of strings. We window it into fixed windows, and then we set an allowed lateness for data on top of that. So in this case, we're allowing data up to 2 days late in terms of processing time, or event time relative to the watermark, sorry. And so if data comes in with an event time that is within 2 days of the current watermark, we can recalculate those panes. In a more complex code example, this is going to look more similar to what you want to do here. We have our same P collection of strings, but in this context, we actually have a couple options with our triggering. So with our windowing, same fixed windows of a minute. But then when we trigger, we set multiple values. After watermark means that we want to emit the pane once the watermark is passed. Pretty typical completeness trigger. But now we have 2 extra configuration options that we want to pass. With early firings, we actually are saying, okay, if we get data before the watermark is passed, we'll emit the pane every minute. We can start doing calculations, what have you. And then you can also set with late firings, which is the case that you are getting late data. And in this case, we are configuring the pane to be emitted after getting any late data. You get one piece of late data, re-emit the pane. and then that same allowed lateness of 2 days. So for a window of 2 days relative to the watermark, you can get your late data and emit it. And of course, before the watermark is passed, you're just steadily updating that pane so you can do calculations on it and see the values that are being calculated within that window before the watermark is actually passed. So we have panes, we're working with panes. How do we manage them a bit better? Because when you specify a trigger, you also have to specify an accumulation mode for the window, because when you're re-emitting panes, you have to decide what you want to do with them. Do you want to make the pane larger? Do you want to discard earlier data? What do you want to do? So accumulating triggers re-emit the data that was previously emitted along with the new data. You can set the accumulating fired panes option when you set the trigger. And the idea is that the pane will just grow with that new data. So if we had an accumulating trigger that fired every 3 elements, you see this first trigger emits 583, second trigger emits 583, and then the new elements 15, 19, and 23. And then the third trigger fires 583, 15, 19, 23, and 9, 13, and 10. So these are all emitted repeatedly. So how you handle that data down the stretch may change further down the pipeline. A discarding trigger only emits the new data it received since it last fired. And this is most commonly used when the downstream transform is doing some sort of aggregation with the panes already. So if you're doing some sort of summation or arithmetic calculation, this is a pretty useful idea. So if you're setting this with the discarding fired panes, what will happen is your first trigger fires, you get the first 3 elements, 583. Second trigger fires, you get 15, 19, 23. You don't get the first 3 elements. And then the third trigger fires, you get 9, 13, and 10. You do not get any of the previous elements. So something to keep in mind with that, well, I'll go back thinking of this. Something to keep in mind with this is that if you're doing aggregations further down the stream, you would want to do discarding, because you would, in theory, be updating the aggregations as you're going as well and receiving panes. So you don't want to receive elements that you've already considered multiple times. That's sort of the motivating example behind wanting to keep discarding that data. So quick shout outs for extra reading. Some of this will look familiar from the previous talk. Streaming systems, the what, where, when, and how of large-scale data processing is a great resource for these concepts, written from the perspective of Apache Beam. There are code snippets in there. It's largely written in Java, lots of great graphics, things like that. And then I also want to shout out the Beam programming guide, where I got multiple graphics for this talk, largely the windowing and some of the code snippets. It's a free online resource on the Beam website with explanations of these concepts, code snippets per language for Java, Python, Go, and some examples even have TypeScript SDK examples. This is a wonderful place to get outlines on how to do these things, why you'd want to do these things, all sorts of things like that. Wonderful resource. Is also an open source page. So if you find something wrong or you want to contribute, we do accept contributions on the Beam repo itself. Thank you so much.